Hello again. We want to talk about inverse trigonometric functions. So we actually use this all the time when we're finding an unknown angle. A simple trigonometric right angle triangle problem. You've got 3 and 4 and you want to know theta. Well, it's obviously tan theta is equal to 3 on 4, so you do tan inverse. And the symbol that we use is this sine or tan or cos with this little -1, which is the inverse symbol. But in other contexts, if I say write x to the -1, that means 1 on x. So it can lead to some confusion with reciprocals. Inverse or reciprocal, what is it? Well, it depends on the context. So to avoid that, in this course, very commonly, we use arcsin x, arccos x, and arctan x for the inverse trigonometric function. And so that's where it's just a kind of a ability to avoid the confusion coming from the inverse. The inverse symbol is not wrong, but tends to be confusing. Now, we should know from our function work that to find the inverse functions, we switch the x and the y coordinates and then rearrange. You also know that graphically speaking, it's reflected in the line y equals x. Now, I'm going to show you the three. Just jump over to Desmos, and I'm going to show you. But if we draw x equals sine y, x equals cos y, and x equals tan y, see what happens. So let's just go across and have a look. So if I do x equals sine y, that's the reciprocal. Not the reciprocal, sorry, I keep saying the wrong word. That's the inverse function. Now there's a problem. This is not a function. Why not? Well, it's not a function because it doesn't satisfy the vertical line test. There are many values. If I drew a vertical line, there would be many times that it would cross the curve. So what this means is we have to restrict the domain of the function to a certain set of values to be able to find it. Now, if I sort of zoom in and kind of are able to match it up, so from there, and then if I just kind of think of it from -pi on 2 to pi on 2, what do I have? Well, this now satisfies the vertical line test. So if I take sine x from -pi on 2 to pi on 2 and find the inverse of that, I can actually get the function arccos. Now, okay, that's sine. So that tells us that we have to restrict the domain. What about x equals cos y? Now, if I go ahead and use the same restricted domain from -pi on 2 to pi on 2, well, there's a problem. That still doesn't satisfy the vertical line test. It goes through twice. But what if I, instead of choosing -pi on 2 to pi on 2, what if I go from 0 up to pi? Well, we see that just backwards, or the negative, opposite of that, reflection of the sine, arcsin, we see that this is now a function as well. So for sine arcsin, we go from -pi on 2 to pi on 2. For arccos, we go from 0 to pi to restrict sine x and cos x. Now, if I then have a look at tan, well, it's sort of, this is x equals tan y, the sort of inverse function. But again, we can't do that. So we've got the pattern repeated over and over again. So I just want to take the middle one, the very first one. So if I restrict that from -pi on 2 to pi on 2, then we see that it satisfies the vertical line test. So those three, with different restrictions, we get these three functions. And you see that arcsin is from, the domain of arcsin is the range of sine, which is -1 to 1. And the range is now from -pi on 2 to pi on 2, which is the restricted domain of y equals sine x. Arccos is very similar, just shifted up, again from -1 to 1, but the range is from 0 to pi. And then arctan, the asymptotes are now horizontal asymptotes at -pi on 2 and pi on 2. And the domain is now everything, all real, whereas the range is from not including -pi on 2 up to pi on 2. So if we go back, I've actually drawn or got a sketch of each one. So we see here the two curves together. the green curve, if I zoom in here, the green curve is y equals sine x. Actually, why don't I actually use green? And we can use the same color. Y equals sine x, but only from minus pi on 2 to pi on 2, restricted domain. And this one here, the purple curve, is y equals arc sine x. Just a little kind of, quite a stumpy little thing, isn't it? It's just kind of only part of the curve, and they cross over at 0, 0, which we, just as an aside, call an invariant point. If I look at it for cosine, the red curve here is y equals cos x, but again, it's from 0, the domain is restricted up to pi, curly brackets, which then gives us the orange curve, which is arc cos x, y equals arc cos x. Now, I'll let you to have a think about what this point is. What's the value of this point? That's called an invariant point. This line is y equals x. That's where it's reflected in. And there's this point that doesn't change. And it's not any value that we've sort of encountered before. So I'll let you kind of have a think about that, see how we go. The third one is, this black line is y equals arctan of x. And the orange line, I don't have an orange pen, I'll use pink, is y equals tan x, but only from minus pi on 2 x to pi on 2. So the important thing you need to get across is that the inverse trigonometric functions have a restricted, well, you have to restrict the domain of the trig functions to find the inverse trig functions. And these three are what they look like. Now, I encourage you to go into Desmos and have a look at them and see how you draw them. It's a reflection here. We can appreciate that that's a reflection. The vertical line has, tan x has vertical asymptotes at pi on 2 and minus pi on 2. Arctan has horizontal asymptotes at pi on 2 and minus pi on 2. And that's kind of what we have. Now, there's a helpful little table in our book here which tells us function arcsine x, definition is x equals sine y, right, what I sketched, but only taking x from minus 1 to 1, and the range y is minus pi on 2 to pi on 2, which is the opposite of the domain and range of y equals sine x. And that's the same for all three. Now, something I just mentioned before, an invariant point, when taking the inverse, is a point on each curve that maintains the same exact coordinate. So 0, 0 is a point on both sine x and arcsine x. That's where they cross over. So we call that an invariant point. Doesn't move when you sometimes called the image. When you put it onto the inverse, it doesn't change. Now, we want to have a look at these three examples, and these are the types of questions we think about. So, in some senses, arc, cos and cos, or arcsine and sine, or arctan and tan, they undo each other. So in some ways we want to think, well, the answer to this, remembering that it's y, the output, the answer to this, we want to write y equals negative pi on 6. Right? If they cancel each other out, we can kind of just cross it out. The problem with that is the definition, right? We could have taken any sort of section of the inverse and being able to do that. But we've decided to take it from 0. We've decided to take it from 0 to pi. Now, this is outside of that range from 0 to pi. So we need to sort of modify this. So I actually have to take it away. But actually, I'll write it so it maintains. It's not that. It's outside range of arccos, right? So we need to think about it. Now, what is cos negative pi on 6? Well, it's going to be the same as cos pi on 6. So it is root 3 on 2. So this actually becomes arccos root 3 on 2, which is actually equal to pi on 6. And that is within the range. So tick. What about this one? again, cos arccos negative a half. Well, tempted to kind of write negative a half. Now, in this case, we can do that because cos is a curve that has no restrictions on its domain or range. The range goes from -1 to 1, so I can just simply write negative a half, right? You could think about it as, okay, arccos of negative a half is, there's two answers you're going to potentially get. It's going to be either 2 pi on 3 or 4 pi on 3. But, again, it's not 4 pi on 3 because the range of arccos is from 0 to pi, so it must be 2 pi on 3, but cos 2 pi on 3 is still negative a half. And then this one here, arcsin, so sine 4 pi on 3. Well, the temptation is just to say, well, they cancel each other out. It doesn't always work, though. You can't do that. It is outside minus pi on 2, 2 pi on 2. It doesn't work. We can't have that. So what we need to think instead is, well, sine, this is going to be arcsine of sine 4 pi on 3 is the same as sine pi on 3. No, it's not, my lies. It's the same, it's the negative of sine pi on 3. So sine pi on 3 is, sine 60 degrees is root 3 on 2. So it's going to be negative root 3 on 2. Arcsine of negative is root 3 on 2. And that is going to be, it has to be a negative quantity. It's actually going to be minus pi on 3. Why is that? Because it has to be between minus pi on 2 and pi on 2. And that is the value, negative pi on 3 is the value that is between those two. Now, this is the last one of chapter 12, exercise 12H. Have a look through. You've got to think carefully about these types of questions, whether the domain and range makes a difference or whether I can simply write it. It depends on partly on the order, partly on the values and the functions that we're doing. So you've got to think carefully about it, following conventions. Okay, see how you go.